Hello my dear friends, welcome back again to our YouTube channel Invisible Threads. Hope all of you are doing well in this difficult period. Please wear masks appropriately and try to maintain social distancing as much as possible. So today in this video I will try to discuss one new topic, mostly on electrostatic potential. So let's begin. So what is potential energy? It is the energy that is stored in an object due to its position relative to some zeroth position. So there are different kinds of potential energy like gravitational potential energy from spring, magnetostatic potential energy, electrostatic potential energy, etc. So this potential energy is stored in an object, and if we remove the external force, the body gains kinetic energy and loses the equal amount of potential energy. So from the energy conservation we can say that the sum of the kinetic energy and the potential energy is conserved. So we can write that. So this is the electrostatic potential. So what is the energy conservation? So it means that the sum of the mechanical energy, it means the sum of the kinetic energy and the potential energy is constant during some work done. So such kind of external forces that makes transfer from potential energy to kinetic energy or vice versa in a body are called conservative forces. So conservative forces means where the energy is conserved. So what is this conservative force? So we can say that the spring force and the gravitational forces are the conservative in nature. We have already, I will discuss in my later videos that this kind of forces are conservative. So from the name we can get to know that the work done through such kind of forces conserve energy. From the following diagram here, we can get the better idea for the conservative forces. So you can see there is two position of the ball here. In this position A, initially the ball is at the position A, and its weight is acting downward due to the gravity. It is mg acting downward, and I took the ball from A position to B position, where the vertical displacement is delta H under the influence of the gravity. Then the work done only depends on the vertical displacement of points A and the B. So this is the vertical displacement is delta H. So the work done depends on the initial and the final position. So the work done does not depend on the path, and it only depends on the initial and the final position. The work done by the gravity is Wg. We can write it as Wg is equal to mg minus of mg, because where does this minus sign comes from? Because the work done by the gravity. So Wg is equal to minus mg times delta H. So we can say it does not matter how complicated the path is from A to B, but the total work done depends only on the initial and the final position, which is A and the B. So we can say that the gravitational force is a conservative one. So let's discuss some properties of the conservative forces. So what are the properties of the conservative forces? It means the force depends on initial and final position only, irrespective of the path taken. So I have already discussed that it depends on the initial and the final position, which is A and the B. Irrespective of the path, I have taken the ball from A to B. In any closed path, the work done by any conservative force is zero. It means, suppose from the previous discussion, if we move the ball from B then back to A, the work done will be against gravity. So it will be plus of mg times delta H. So during the closed circular path, the total work done will be zero. So in any closed path, the work done by any conservative force is zero. And which will be the next one? Work done by the conservative force is reversible. It means, suppose in this direction, this is the work done by the gravity. So if I took the ball from B to A, this will be work done against gravity. So if the force does not follow any of the properties, any of the three properties, it is said to be a non-conservative one, like the friction. So friction is a non-conservative force, as there is, so you can say that the friction is a non-conservative force as there is change in mechanical energy, sum of potential energy and kinetic energy during the work done. Because where does this excess energy goes out? So because the excess energy, some energy is dissipated in the form of the heat. So now from our previous discussion, we are now on the way to prove that the gravitational force, the electrostatic force is also a conservative one. So there must be a quantity called electrostatic potential in analogous to gravitational potential. So like gravitational or mechanical potential energy, we must define a reference point from which we can define electrostatic potential energy. So this is the origin, and there is a plus q charge is located. and at the point A there is q prime charge is there. I want to bring the charge q prime from A to B. So we have fixed the origin charge at the origin, and it will produce its own electric field. You can see that the charge will produce its own electric field, and we want to bring the test charge q prime from point A to B. We need to put some external force to overcome the electrostatic force, because the plus q charge will produce some electric field. So every time while I am bringing the charge q prime from A to B, there will be some opposite forces, which is the repulsive forces. So I need to put every time some external force in balance of this electrostatic force. So there will be every time the repulsion forces. So I choose that the q prime is less than q, such that while bringing from q prime, this q prime from A to B, it will not disturb the original position of q. So I choose that q prime is very less than plus q value, because it does not, the q prime does not hamper the original equilibrium position of plus q. So the process was done very slowly. So I took the charge q prime from A to B very slowly. The external force that we need to apply against the electrostatic force, what it will be, F external is equal to minus of F electrostatics. So while bringing the charge q prime from A to B, every time I need to put the external force which is equal and opposite to the electrostatic force. So F external is equal to minus of F electrostatics. So we can assume that there is no acceleration of the charge q prime from A to B. At the moment that charge q prime is brought to B, if we remove the external force, suppose I bring the charge q prime from A to B, at the point the charge reaches to B, if I remove the electrostatic force, if I remove the external force, the electrostatic force due to this plus q charge will keep away the q prime, and the potential energy that has been stored in the q prime will get converted to the potential energy, get converted to the kinetic energy. So in this scenario, both the sum of the kinetic energy and the potential energy is conserved. So we can say that the electrostatic force is conservative in nature. So I am saying again that at the moment I bring the charge q prime to B and I remove the external force, so there will be electrostatic force acting on this q prime for the point B, and it will try to keep the charge q prime away from this point. So the potential energy that has been stored in the q prime, due to its movement from A to B, it will get converted to the kinetic energy. So the work done from A to B, F external dot dr, this is the work done. This is the dot product, this is the scalar quantity. It means the minus of A to B lower limit to upper limit Fe dot dr, because F external is equal to minus of F electrostatic. So we can say that this work done is against the electrostatic repulsive force and gets converted to the potential energy. So we can write that, we can say that at any point inside the electric field, any kind of charge have its own potential energy, and any kind of work that has been done, it means the change in potential energy from moving one point to another. So we can write that the work done W, I brought the charge q prime from A to B, so the work done is WAB, is equal to change in potential energy. It means the final point potential energy UB minus of UA, final position potential energy minus of initial position. So work done, we can write this is the change in potential energy under the electrostatic force. So what are the conclusion? So work done under electrostatic force under any electric field by moving any charge from one place to another depends on initial and final position and is independent of path. So electrostatic force is conservative in nature, and the change in the potential energy is significant. The change in the potential energy is significant rather than its actual value, because change in potential energy is the electrostatics work done under the against the electrostatic force. So this is our next page. So we can always choose our origin in such a way that the potential energy is zero at the infinity. Suppose I brought in the previous diagram, you see that I brought the charge q prime from A to B. If the point A I choose at infinite distance, and I assume that the potential energy at the point A, which is at infinite distance, is zero, so the work done is equal to change in potential energy is equal to minus of A to B Fe dot dr is equal to minus of, I choose A to be at infinite distance, so minus of infinity to B Fe dot dr is equal to W of infinity B is equal to UB minus U infinity. I choose U infinity to be 0, this is 0, so this becomes is equal to UB. So I have got that the potential energy at any point for charge Q, I can write it as like that. There is the work done on to bring the charge Q from infinity to that point under the electrostatic force. So suppose at some point in the electrostatic area, electric field, I need to find the potential energy. It means if I bring some charge Q from infinite distance at that point under the electrostatic force, the amount of work that has been done, it indicates the potential energy of that point. So we can say that the potential energy of a charge Q at a point inside the electric field, it means if we bring the charge from infinite distance at some point inside the electrostatic field, how much work needs to be done is the measure of the potential energy. So up to now we have understood that the potential energy of any charge at any point inside the field, it means the amount of work done to bring the charge from infinite distance at that point against the electrostatic field. So if we consider to bring some unit positive charge, instead of plus Q charge, if we try to bring some unit positive charge such that the work done does not depend on the charge value. So VB minus VA, this is the, we define as the potential, is equal to UB, this is the change in potential energy divided by Q. So we can say that the electrostatic potential at any point, what is the electrostatic potential at any point is equal to work done to bring unit positive charge, 1 unit of positive charge from infinite distance to that point under the electric field is called the electric potential. So while we can say that the potential is 0 at infinite distance and the electrostatic potential at any point P, this means that we need to bring out some unit positive charge from infinite distance to a point P. It is the measure of the electric potential. Now we try to calculate the electrostatic potential due to some point charge. So this is the diagram, this is the origin here. For simplicity, in the origin I choose the plus Q charge to be located, and I try to find the electric potential at point P, which is a distance of r away from the origin. So OP is equal to r vector, and initially suppose the charge is the 1 unit of positive charge is at the point P prime. So OP prime I choose to be at r prime position vector, and the plus unit of positive charge is moving from P prime to this point. So delta r prime is equal to magnitude of delta r prime times the, in this direction this is the r cap, this is the r prime cap. So as the charge is the 1 unit of positive charge is moving from right to left, so this will be minus of r prime cap. So at that point, so you can see at point P prime, the electrostatic force on 1 unit of positive charge, what it will be, Q divided by, this is Q1 Q2 from the Coulomb force. We know that the Q1 Q2 divided by 4 pi epsilon naught r square. So Q times 1, this is the 1 unit of positive charge, divided by 4 pi epsilon naught r prime square time r prime cap, this is the r prime distance, along OP unit vector r prime. We choose the r prime cap is acting the unit vector along OP. While moving the charge a small distance delta r prime towards Q, so I initially the 1 unit of positive charge at P prime. So suppose after some time the charge reaches to in this point, suppose this is P double prime. So at P double prime it moves a distance of delta r prime. So the work done will be delta W is equal to Q times 1 divided by 4 pi epsilon naught r prime square r prime cap dot delta r prime. Again delta r prime is a vector quantity is equal to magnitude of delta r prime times its unit vector, which is minus r prime cap. So it will be Q delta r prime divided by 4 pi epsilon naught r prime square. So this is the elementary work done. So this is the elementary work done while moving the charge from P prime to P double prime. But initially the 1 unit of positive charge is at P prime. I need to bring the charge at the point of P. So the total work done by the external force, what it will be, from r prime is equal to infinite, and I need to bring, initially the charge was at, our main target will be to bring the charge from infinite to a distance of r. So the total work done will be, the lower limit will be infinity to a final limit of r with respect to the origin. So it will be minus of q by 4 pi epsilon naught r prime square dr prime. So if we integrate it, it becomes q by 4 pi epsilon naught r. So due to this point, so you can see, due to this plus q charge at point P at a distance r away from the charge plus q, the potential comes out to be Vr is equal to q by 4 pi epsilon naught r. So we can see that if r tends to infinity, the Vr tends to 0. So the potential tends to 0 if we go far away from the charge. And when the charge is negative, so I choose the charge to be positive. If the charge is negative, the potential is also negative. So from the electric field and the potential, if we compare between them, the electric field is the red line. You can see the electric field varies as 1 over r square for the point charge, and the potential varies as 1 over r. So electric field is more steeper and the potential is less steeper. So this is the comparison of the electric field and the potential with the distance. So my friends, I am concluding my today's discussion here. If you have any kind of question, don't hesitate to let me know in this video's comment section. Stay updated and keep supporting Invisible Threads. Thank you and have a great day.